Welcome back to this explainer brought to you by Forge College. Today, we're continuing our Programming with Solana track, diving into advanced Solana program structures, and specifically, we're mastering program architecture. Now, if you remember our last lesson on the foundations of program architecture, we separated our hot and cold paths. But today, today we are rolling up our sleeves to fix those nasty hot path bottlenecks. We're going to take those abstract performance streams and, turn them into concrete, high-speed reality.
Okay, let's jump right into this. Why is our supposedly super fast Solana program sometimes moving like a snail in peanut butter? Well, if you recall our last lesson, we talked about the underlying causes of these bottlenecks. Imagine you've got 10,000 eager users, right? And they're all trying to hit the exact same account at the exact same millisecond. It is literally like forcing a massive 10-lane superhighway through a single-lane toll booth. The Solana runtime itself is incredibly fast, but if your program design forces it to process transactions one by one just because they're all trying to modify the exact same piece of data, well, you're going to get a traffic jam. Period.
So, here's our schematic for today's lesson. 1. The architecture traffic jam. 2. Your scalability toolkit. 3. Fixing a DEX order flow. 4. Parallel code in action. And finally, 5. Principles and trade-offs. Let's get to it.
Section 1. The architecture traffic jam. First things first, we need to clearly define the failure.
Before we write a single line of code, we absolutely have to define the mechanical failure we're trying to engineer our way out of here, which is account contention. So when you have overlapping writable access, you essentially force the network to pause all of its parallel processing magic and serialize those transactions. It's kind of like 10 people fighting over a single pen just to write a novel. And alongside that, you've got the expensive deserialization of massive account data structures. The runtime literally has to load and parse all that data before it can do anything. So, together, runtime account locking and expensive deserialization, they are the absolute enemies of scale.
All right, moving to Section 2, your scalability toolkit. Let's look at some architectural levers.
Let's crack open our toolkit and see how pulling some specific architectural levers completely bypasses these bottlenecks. Now, what's really fascinating here is that every single solution forces us to trade just a bit of simplicity for a massive, and I mean massive, boost in throughput. Let's look at the first 3 tools. Number 1 is partitioned state. Instead of one giant monolithic account, you break it up into lots of smaller ones. This drastically reduces contention and enables parallel transactions. The trade-off, though, you've got more accounts to manage and pay storage for. Tool 2 is read-only separation. Look, if you don't absolutely need to change the data, don't ask for our write lock. This lowers serialization cost, but does require some really careful API design. And tool 3 is batching and settlement. Bundle up those frequent, small changes. It lowers your per-operation compute, but, it introduces a little bit of latency since users do have to wait for that batch to settle.
Rounding out the toolkit, tool number 4 is off-chain matching. If per-transaction compute or tricky cross-program coordination is your main roadblock, pushing that heavy matching logic off-chain is for sure your best bet. It dramatically shrinks on-chain compute. The catch? You now need reliable, trusted off-chain infrastructure. And finally, tool number 5, modular programs. By designing small, single-responsibility programs, you make it crystal clear exactly what program owns what state. It simplifies your locks, though actually you might end up with more cross-program invocations to audit down the line. Moving right along to Section 3, fixing a DEX order flow. Let's actually apply this toolkit.
Let's simulate this cool kid out in the wild on a high-frequency decentralized exchange, a DEX that needs to process thousands of orders a second. Imagine designing it with one global order book account holding everything together. Honestly, having a monolithic account like that is literally like 10,000 people trying to write in the exact same diary at the exact same time. It's a total disaster. Now contrast that with partitioned state. Here, we create program-derived addresses, or PDAs, per market and per user. Now, partitioned state gives everyone their own independent journal. And because they're writing in different books, the network can process all those transactions concurrently. It's a total game changer.
And this brilliantly illustrates our step-by-step blueprint for optimization. Step 1, find the hotspot. Use your logging to see which accounts are constantly locked up. Step 2, shatter that state into shards using the PDAs we just talked about. Step 3, trim the instructions down so they're lightweight and only ask for exactly what they need. And step 4, if the math is getting a bit too heavy, let your off-chain engines do the heavy lifting and just rely on the blockchain for the final settlement and verification.
Okay, Section 4, parallel code in action. Let's do a quick code walkthrough. We know the theory, so let's inspect the actual mechanics of a real Anchor implementation. This is really where the magic happens between the client and the program. First off, keep shared accounts, like your market configuration, non-mutable. You're basically telling the runtime, hey, I'm just looking, I don't need a lock. Second, use a mute flags vector. By making the client do a little bit of homework to submit a compact map of what exactly needs mutating, the program gets a cheat sheet. And that allows our third point, iterating through remaining accounts dynamically. We can iterate through the list of accounts at runtime and, point 4, which is huge, skip the expensive deserialization for the read-only paths and only write when flagged.
Listen, if there is one single thing you write down today, it's this. Avoid unconditional deserialization of large structures. It is absolutely vital that you keep read-only accounts truly read-only at the runtime level. Think about it. If you force the runtime to unpack massive data objects every single time, even when nothing is changing, you're just burning compute and destroying your throughput. Keep those operations lightning fast by only unpacking what you're actively changing. I mean, don't pay for premium luggage fees if you only need to pack a toothbrush, right?
Finally, Section 5, Principles and Tradeoffs. Let's wrap this up. As we wrap up this blueprint inspection, let's distill the whole shebang down to the core principles you absolutely need to memorize. Minimize contention, reduce compute, make it read-only. These are your 3 pillars. They are the golden rules of Solana program architecture. They take all those abstract performance dreams you have for your dApp and convert them into concrete, practical design constraints. So every time you write an instruction, you need to be asking yourself, am I creating contention? Am I burning unnecessary compute? Can this be read-only? So I'm going to leave you with this question to ponder. As we head into our next hands-on lesson where we actually build these resource optimization patterns, ask yourself, which single trade-off will unblock your hottest path without over-engineering your entire system? Remember, you really don't need to use every tool in the toolkit at once. Just pick the one that solves your specific bottleneck. Thanks so much for watching this explainer. Head over to forge.college to learn more about this and other incredible Web3 topics. We'll see you in the next lesson.